100 megawatts. From one pump smaller than a car engine. No boiler, no dam, no reservoir. That's more electricity than a small hydroelectric dam pushes out, and it fits in your arms. Here's exactly how it works. A big liquid rocket engine drinks propellant like nothing on Earth. Hundreds of kilograms of fuel and oxygen every second. Gravity can't pour that fast. Tank pressure can't push that hard. Starve the engine and it dies. So here's the real puzzle. How do you force tons of fuel a second into a chamber that's already shoving back with brutal force? Start with the wall the fuel has to beat. Inside the combustion chamber, pressure runs enormous, roughly 7 to 20 megapascals, which is about 1,000 to 3,000 pounds on every square inch. Picture the pressure at the bottom of the ocean, then stack a few more oceans on top. Now the catch. To flow into that chamber, propellant has to arrive at even higher pressure than the chamber itself. Water only runs downhill. Fuel only flows toward lower pressure. So it must show up pushing harder than the fire pushing back. But the tanks can't help much. To stay light enough to fly, the tanks hold only a few atmospheres, barely more than a scuba cylinder. That's the gap. On one side, tanks at a few atmospheres. On the other, a chamber demanding thousands of pounds per square inch. And you're not sipping. A first-stage engine can swallow hundreds of kilograms of propellant every single second. A bathtub's worth of fuel and oxygen gone in a blink. Something has to grab that low-pressure river and slam it up to chamber-beating pressure, at full flood without pause. That something is the turbopump. So how does one spinning part bridge a gap that big? Here's the muscle. Inside the pump sits a bladed disc called an impeller, and it spins fast, tens of thousands of times a minute. Propellant pours into the center, the blades catch it, and centrifugal force flings it outward hard against the pump's outer wall. Think of swinging a bucket of water on a rope. The faster you whirl, the harder the water presses the bottom. Same trick, just violent. That outward slam is pressure. Feed it in gently, whip it around, and it leaves the rim shoving far harder than it entered. Output can climb past 20 megapascals, more than the chamber demands. The gap is bridged. But one impeller can't do the whole job, because the engine burns two very different liquids. Fuel and oxidizer have different densities. Liquid oxygen is heavy and dense, kerosene and liquid hydrogen far lighter, so one pump geometry can't move both well. The fix. Separate pumps often on the same shaft or extra stages, each tuned to its own liquid. Dense oxygen gets its pump. Light fuel gets its own. Each arrives at the chamber at exactly the pressure and flow the fire needs. Which raises the obvious question. Spinning metal that fast, flinging tons of liquid a second, takes staggering power. Where does that power come from? Now the source of the muscle. Bolted onto the very same shaft as the pump is a small gas turbine. A bladed wheel that hot gas blasts through, spinning it like a pinwheel in a blowtorch. This little wheel is where the 100 megawatts is born. But a turbine needs hot, high-pressure gas to spin. Where does that come from mid-flight? The engine makes its own. It skims off a slice of the propellant it's already carrying and burns it in a small chamber all its own. A gas generator, or on hotter designs a preburner. That side burn produces a furious stream of hot gas, and that stream is aimed straight at the turbine blades. Follow the chain. Hot gas spins the turbine. The turbine spins the shaft. The shaft spins the pumps. One shaft, one spinning line, and the power flowing down it is genuinely gigantic. Around 100 megawatts on a big engine, more than a small hydroelectric dam produces. From a machine you could carry. That's the power density that makes rockets rockets. No other engine its size comes close. But burning propellant just to run the pump has a cost. That slice of fuel does its job, then what? The answer splits rocket engines into rival families. Here's the fork in the road. That slice of propellant burned to spin the turbine. What happens to its exhaust afterward decides how good the whole engine is. The simple path is the open cycle, also called gas generator. It spins the turbine, then dumps the turbine's exhaust straight overboard through a side pipe. Easy to build but wasteful. A little of your precious propellant leaves without ever fully joining the main fire. The clever path is the closed cycle. Staged combustion, or its extreme cousin, full flow. Instead of throwing that exhaust away, it routes it back into the main chamber to be burned again, squeezing out every last bit of thrust. The Space Shuttle's RS-25 and SpaceX's Raptor run closed cycles. Nothing wasted. But nothing is free. Feeding turbine exhaust back into a chamber already at thousands of pounds of pressure means the pumps must push even harder still. And remember what's crammed together in this one spinning machine. Liquid oxygen colder than 180 degrees below zero flows millimeters from gas hot enough to melt steel. Metal spins so fast the blade tips near the speed of sound. Cryogenic cold and furnace heat, separated by a wall thinner than a coin. That knife edge is why turbopumps are among the hardest machines humans build, and why so few nations build them at all. Now watch the whole machine click together. A sliver of propellant burns in a small side chamber, making hot gas. That gas blasts a turbine wheel. The turbine spins a single shaft. The shaft spins the pumps. The pumps grab low-pressure fuel and oxygen from nearly empty tanks and hurl them into the main chamber at thousands of pounds per square inch, harder than the fire pushing back. Hot gas turbine shaft pump high-pressure propellant chamber. One chain running thousands of times a second. And the power sprinting down that shaft is about 100 megawatts, more than a small hydroelectric dam from a pump you could lift. That's the secret hiding inside every big liquid rocket. Not the flame you see, the pump you don't. It's the reason a machine the size of a person can feed a fire that lifts millions of pounds off the ground. Compact in, colossal out. That is the turbopump. So the pump feeds the fire. But that fork in the road, open cycle versus closed, is where rocket engineering gets truly wild. Next, we open up the cycles themselves. Gas generator versus staged combustion versus full flow, and why Raptor's full flow design is such a big deal. Subscribe and let's open that box next.